standard cell potentials and standard reduction potentials. This is the electrochemistry lecture part 3. Let's talk about standard cell potentials first. And you'll see this represented as delta E naught cell, sometimes just delta E naught, or equivalently E naught cell without the delta. All of those generally are the same thing, so they're equivalent. And what it represents is the potential difference between the two electrodes in the cell under standard conditions. So standard conditions are represented with this naught. For all aqueous solutions, the concentration would be 1 molar. If a gas is being bubbled through the solution, then the pressure would be 1 atmosphere. And generally, the standard conditions include the temperature at 25 degrees C. Now, when the cell potential is positive for a cell, then that means that that reaction happens spontaneously. A little later on, we're going to see how that relates to delta G and see how a positive cell potential results in a negative delta G, which means we have a spontaneous reaction. In this spontaneous reaction, electrons flow from the anode to the cathode. And this cell potential can be calculated using something called standard half-cell reduction potentials, or sometimes just called standard reduction potentials. And these are represented with E naught red, so red for reduction. That's how we represent standard reduction potentials. So here's a table that gives you basically a nice example, a nice set of examples of standard reduction potentials. There's a lot more of these. There's a big chart in your textbook. Often they're in an appendix at the back of the textbook, or you can find tables of them online. The higher the reduction potential, so for instance, looking at the silver plus to silver metal reduction, the higher that potential is, the more that species wants to be reduced. So that means it's easier to reduce silver plus than it is to reduce iron 3 plus to iron 2 plus. So 0.80 to 0.77. It's easier to reduce tin 4 plus to tin 2 plus than it is to reduce lead 2 plus to lead metal. So basically, the higher the reduction potential, the more positive that reduction potential, the easier it is to be reduced, and we call those oxidizing agents because they oxidize something else. Now, the lower the reduction potential, the more that species actually wants to be oxidized and get rid of those electrons, and we call these reducing agents. So down at the other end of the spectrum, we have zinc 2 plus going to zinc metal, and that reduction potential is negative 0.76. Highest reduction potential, lowest reduction potential, at least on this chart. Easiest to reduce, silver plus. Hardest to reduce, zinc 2 plus. Generally, elements down in this range with these negative cell potentials are going to be found in the anode position. So the partner in an electrochemical cell with the higher reduction potential is going to be the cathode. Hydrogen gas can act as either a reducing or oxidizing agent. So looking at it right here, right smack in the middle, we have 2 hydronium and 2 electrons, and we're going to get hydrogen gas and 2 waters out of that. Under standard conditions, that standard reduction potential is set to 0. So I'll talk a little bit more about that in a few minutes. But that's basically the middle point. And every other standard reduction potential is measured relative to this reaction. So generally, hydrogen gas is an oxidizing agent when combined with metals, or a reducing agent when combined with nonmetals. A little bit more about this standard hydrogen electrode, represented with SHE, or She. And basically, you have hydrogen gas at 1 atmosphere, and we're going to bubble that through this 1 molar HCl solution. So 1 atmosphere H2 gas bubbles through this HCl solution. We have a platinum electrode. Platinum is inert, and so it's serving as a solid surface for this reaction to take place. Electrons on the surface of the electrode combine with each H plus in solution to produce hydrogen gas. Now, The standard hydrogen electrode is actually used to determine the standard reduction potentials for all of the other elements, all of the other reactions as well, because sometimes you can have more than one reaction for each element. Now, the standard hydrogen electrode was chosen as basically the zero potential electrode, and this is under standard conditions. So here's another way to write it, and we saw it with hydronium earlier, but we have 2H plus aqueous 1 molar, standard conditions. 2 electrons are required to reduce to hydrogen gas, and that's at 1 atmosphere. And the standard reduction potential for that reaction is 0. The potentials for the rest of the half reactions are measured relative to the standard hydrogen electrode. So that's important to remember. Here's a picture of what happens when we want to determine the potential for copper 2 plus going to copper metal. We saw this in the Daniell cell. So here's our standard hydrogen electrode set to 0. It's the anode. Electrons are going to flow through our voltmeter, and we're going to measure a 0.337 volt reaction. And so that will be the cell potential for this copper 2 plus copper half cell. So remember the Daniell cell. We have already talked about these half cell potentials. The reduction potential for the cathode is 0.34 volts. You can find that on the chart. The reduction potential for the anode is negative 0.76 volts. So again, use your table of standard potentials and find both of those on there and make sure that your numbers match and make sure that you know how to use that table. Now, what we want to do to get the overall cell reaction is add the two reactions. And let's add the two half reactions in the Daniell cell, basically as practice, and we're also going to calculate the cell potential for the Daniell cell. We'll do that explicitly. Remember, the lower reduction potential element is going to be the anode. The higher reduction potential is going to be the cathode. So the anode is going to be zinc metal going to zinc 2 plus with 2 electrons. That's the reaction happening. Remember, we're dissolving that anode. And the reduction potential for that from the chart is negative 0.76 volts. Now for the cathode, we're going to have copper 2 plus ions in solution. They're going to gain 2 electrons, and copper metal is going to be deposited on that electrode. And again, using the table of standard potentials, we see that the reduction potential for this reaction is 0.34 volts. Now let's get the overall reaction, because we're going to need this later on for the Nernst equation. So the first thing we're going to do, see the arrow on both sides, it's not exactly in the same place, so it can be a little hard to see, but we're going to cancel out the electrons on both sides of the equation. So electrons in the product side, electrons in the reactant side, and now we're just going to write down what we have left. So zinc solid and copper 2 plus goes to copper solid, which is right here, and zinc 2 plus. So that's our reaction. Zinc solid going to zinc 2 plus. That squares with what we saw in the Daniell cell, where the zinc electrode is dissolving. Copper 2 plus goes to copper metal. That also squares with copper metal being deposited on the copper electrode. So how do we calculate the standard cell potential, delta E cell? And so remember, all of these notations are the same, delta E naught cell, or just E naught cell. And we get all of them in the same way. We take the reduction potential for the cathode, so make sure you identify which is which first, and you subtract the reduction potential for the anode. So for the Daniell cell, 0.34 volts for copper, that's the cathode, and then minus, so remember, the value for the cell potential for the zinc reaction in the anode was negative 0.76 in the Daniell cell. Okay, and we can find that on the chart. We're just going to translate it directly from the chart. So 0.34 minus 0.76, that's going to make this term positive. We're going to end up with 1.10 volts overall for the cell potential. Now there's another method, and if you want to ignore this, go ahead and turn off the video right now and just go to the next part. If you're interested, it's just another way to think about it, and I'll just give you a little bit of extra information. And this is the way I like to calculate it, but I've been doing this a while, and so it makes perfect sense to me. But again, it can be very confusing. So if you're happy with the other way, and it'll always work. So the second method you could use is calculating the cell potential by using the reduction potential for the cathode and the oxidation potential for the anode. And you might be thinking, oh no, I didn't see oxidation potentials anywhere. And actually you didn't. But if you reverse the reaction, like we have to do at the anode, and we have an oxidation reaction instead of a reduction reaction, we also reverse that potential. So the oxidation potential, the oxidation half reaction, is actually, that value is just equal to negative whatever the reduction potential was. So remember, in the previous method, you subtract standard reduction potential of the cathode minus standard reduction potential of the anode. A lot of times that's going to give you a positive term here. Instead, you're just going to switch that sign right away, and then you're just going to add them together. So when you reverse that half reaction for the anode, you're going to reverse the sign of the half cell potential, and you're going to get an oxidation potential instead. So here's the reduction potential for the cathode, and now we're just going to add, and we reverse the reaction at the anode, so now we have 0.76 positive instead of negative, and you can see we get the same answer. So again, another method to do exactly the same thing. The thing I just asked you to do, don't do both. Don't subtract the two potentials and reverse the anode, or else you will get the wrong answer at that point. So pick one method or the other and use it consistently. Okay, so the next thing we're going to talk about is the relationship between free energy, equilibrium constant, and the cell potential. And that's going to be electrochemistry part 4.